Okay, as for the assignment that you have in front of you, we're switching gears a little bit, getting away from the patterning and the logic and stuff like that, and getting into a little bit more of the calculations. And today's calculations is going to involve measurements of two-dimensional shapes. Okay, and particularly when we talk about measurements of two-dimensional shapes, that basically usually means things like perimeter and circumference, and then of course area. And if you can work with perimeter and circumference and area in two dimensions, then there is really not much difference between working with those in two dimensions and working with three-dimensional shapes with formulas like surface area and volume, just different formulas. Okay, going to go through the kind of a step-by-step on this with you. I'm not going to tell you, how to do it or work through the calculations with you, but I do want to go over these questions that are there, discuss these shapes in a little bit more detail, because like I said, there's only a couple of questions down at the bottom, but it is far more complicated than just two questions down at the bottom of the page. So let's take a look at this. At the top it says an aerial view of the rooftops of downtown Multiplex City is shown in the diagram. The rooftops of these 6 buildings are composed of the following figures. Now after the figures you have several bullet points that follow. Yours looks different than mine does on the screen because I distributed a lot of the information around to kind of help it make a little bit more sense. Okay, so one of the bullet points that you are given is that the dimensions of downtown Multiplex City are 750 feet by 600 feet. Okay, that probably seems like important information in the sense that they may ask us about the total area of Multiplex City or maybe the perimeter, and then those measurements of the entire of this shopping mall or whatever this thing is. We may need that. Okay, so file those away somewhere. The remaining bullet points are information about these shapes that we are being given. Okay, and just kind of going from left to right. On the top left, one of the bullets says you have a regular hexagon with sides of 125 feet. Now, things to keep in mind as far as a regular hexagon. Obviously, we have the word regular, and regular means that we have, all our sides are going to be the same. We're going to be equilateral, and we will also be equiangular, okay? And just in case that is important to the problem. But the word regular, you've got equilateral, you've got equiangular. Now, something really important to keep in mind with a regular hexagon, hexagons have all kinds of cool little properties that go along with them. Now, if we found the need to calculate the area of our regular hexagon, that formula is going to call upon the apothem of the regular hexagon. And of course, we remember that our apothem is from our center point directly over to our side so that it forms a 90-degree angle right there. Now, clearly, we're not provided with that information based upon what they gave us. But again, one of the main properties of a regular hexagon, what happens if you start from that center point and bring 2 radii into the problem along with it? Remember something special about those triangles that are built between the sides and the radii? Okay, the property is that in a regular hexagon, it is built out of 6 regular triangles. Okay, so what I've got outlined right there in blue, that is a regular triangle, meaning if the side length is 1 tick mark, it's also going to force those 2 radii to be 1 tick mark. So if you have 125 feet on one side, you also have 125 feet on each of the radii. Okay. That can be important because we can possibly set up a right triangle inside of there. We can use Pythagorean theorem that can help us find our apothem if we need it. Okay, so there's a little information on that one. Below that is a regular pentagon with sides of 125 feet. Now that's fine. We know that regular, once again, means it's going to be equilateral, also going to be equiangular. Okay, but a critical difference between what a regular hexagon was able to do and what a regular pentagon will do arrives here. We don't get the same property when we bring that triangle into play. Okay, this is not a regular triangle. So whatever's going on with this bottom edge, that side edge, 1 tick mark, those other two guys, those radii that are in there, they are not going to be the same length as the side. Okay, that equilateral idea is specific to a regular hexagon, not a regular pentagon. Okay, so one thing to keep in mind possibly is that if you do find the need to come up with the apothem for this particular shape, is we may need to figure out a way to do that, and we may not have enough information to do Pythagorean theorem. Okay, so one thing you can do is, of course, remember that in any figure, if you start at a given point and you rotate all the way around the center point and come back, how many degrees worth of rotation is that? It's 360 degrees. Can you take that 360 degrees and divide it up amongst the different intervals that are inside of there? Yeah, you can. And if you divided it up far enough, you'll eventually end up with an acute angle inside of a right triangle, and then you can do SOHCAHTOA. You can set up a sine function or a cosine function or a trig function, and that may be able to help you target that apothem if you need to know its measurement. Okay, so a little bit of information there. The two center figures are easily the most complicated figures that we have. The one at the top, the bullet point that's down at the bottom, says it is a composite shape consisting of an equilateral triangle and an isosceles trapezoid. Okay, the bases of the trapezoid are 125 feet and 75 feet. The leg of the trapezoid is 150 feet. Okay, that's just a matter of kind of tearing the figure apart a little bit, applying the numbers wherever they go. Okay, so let's have a look at that real quick. It says it's composite, consisting of an equilateral triangle and an isosceles trapezoid. Well, I think everybody can clearly see that there is the kind of the division line that the composite shape is making. Okay, so you have an equilateral triangle, it says. Okay, so you got equilateral up there. And then it says an isosceles trapezoid. Okay. Well, a trapezoid, of course, is going to establish that in this quadrilateral underneath, there is exactly one set of parallel sides. Okay, well, obviously, okay, your parallel sides are there. And it also says that this trapezoid is isosceles. Okay, so what does isosceles mean? Okay. Yeah, we're going to get two sides that are the same, at least two sides are the same, but when they pull isosceles on us for a trapezoid, okay, that is going to refer to those non-parallel sides there. They are going to have to be congruent. The information goes on to speak of bases and legs. Well, in a trapezoid, okay, what's the difference between bases and legs? Which ones are the bases going to be? They're the ones that are parallel, exactly. Okay, so when it talks about bases, okay, it is giving us information about those measurements. And then when it speaks of legs, it is giving us information about those measurements. Okay. The one underneath is probably the worst figure on the page, and its bullet at the bottom says it's composite of semicircles, rectangle, and a rhombus. And I think it's probably pretty clear to everybody that you got, semicircles going around the outside. And if you wanted to get absolutely technical, you've got an entire circle, right? You got half a circle on the left side, half circle on the right, like Moses did his best Red Sea imitation, split that circle in half. And then there is a rectangle that's jammed in between them. Okay, so that's the two semicircles in the rectangle that the problem talks about. My board's kind of glitchy, so it didn't draw very well. And then it also talks about a rhombus. Okay, well, the rhombus is that guy that's sitting in there in the middle. It goes on to say that the dimensions of the rectangle are 125 by 100. The rhombus forms an open atrium with diagonals of 50 feet and 25 feet that is also to be outlined, and we'll talk more about that here in a second. Does everybody understand what an atrium is? Do you know this word? You ever been in a building that, particularly buildings that have elevators on the inside of them? A lot of times there's an open air area, and they have trees sometimes inside of the building and stuff like that, like benches, and it's just open, a lot of plants and trees and stuff like that. And sometimes it's open all the way to the sky, so the building is kind of built in just like a perimeter, and it's open on the inside. Well, that area inside of there where they have all the plants and trees and stuff like that, that open area is called an atrium. Okay, so that's how come you've got that unshaded area on this building right there. So apparently they've got this building around the outside, but there's this hole coming down through the middle of it that they're calling an atrium. Okay. So anyway, there's kind of some information on that shape. The easiest thing probably on the page is the circle over there on the top right. It says a circle with a diameter of 200 feet. Using that diameter, we ought to be able to solve for any piece of information that we would like for that circle. And then the final one, the bullet establishes that it is a parallelogram with a longer base of 175 feet and a height to the longer base of 150 feet. Now the wording on that's a little bit strange, so I wanted to kind of share with you what that actually means. Parallelogram with a longer base of 175 feet. So they give us this piece of information, and then they say a height to the longer base. Now I was pretty concerned that a lot of people would misread what that means. Okay, and a lot of people would just say, oh, that's the other side of the trapezoid, or the parallelogram, and it's not the other side of the trapezoid. They said it was a height. Okay, heights occur when you're perpendicular to one of your sides. Okay, so they established that the height to the longer base is 150 feet, if I remember correctly. Anyway, they also come back and they say that the base angles, okay, that's something we haven't talked about much in quadrilateral discussions, okay, but anyway, what they're saying here is they say that where'd it go? I've lost it. The base angles of the parallelogram are 80 degrees and 100 degrees. Those are the two different angles that are in the parallelogram. Okay, so there's your 100 degree, okay, the larger of the two angle measurements. And then you, of course, have the smaller of the two angle measurements there, 80 degrees. Okay, now why would they give you that information? Well, when it comes down time to get the perimeter going around this thing, or if you have to find the perimeter, as you can see, we're missing this left slanted side, and then the right slanted side will be congruent, but we don't have that information. But can you see a right triangle in there? Okay, you got a right triangle in there. You might be able to tackle Pythagorean theorem with it if you can find enough information. But if you cannot find enough information, well, that 80-degree angle is acute. Okay, you have an acute angle in a right triangle. Once again, when that happens, you can set up SOHCAHTOA, use sine, cosine, tangent, and that will help you be able to solve for your missing side length on your parallelogram. Okay, so all that information is what they provide you, and that is a lot of external information. They've given us a lot of information, but they've left a lot of things open as well. Okay, there's literally countless questions that I think they could ask you at this point. So let's look at what they do ask you. Okay, the first question, it's multi-part. Okay, but it says the roof line of each building is to be outlined with lights. If a strand of lights covers, and I believe your paper says 5 meters, I went ahead and converted this for you. Okay, the conversion is 16.5 feet. The problems are going to be complicated enough without you having to worry about a conversion from metric to standard measurements. So go ahead and change your paper, put 16.5 feet. If a strand of lights covers 16.5 feet, how many strands of lights will be needed to outline the roof lines of downtown Multiplex City? Now, that's not a difficult sounding question, but as you're about to discover, hopefully follow along with me, there's a lot of information that has to be taken into account if you're going to do more than just guess at this question. Okay, the question goes on to ask, or to state anyway, round your answers to the nearest whole number. That's okay, that'll help you out a little bit. You don't have to mess around with decimal points for long. And then if the rooftop of each building was to double in size, what effect would it have on the number of strands of lights needed to outline the roof lines? Explain your reasoning. So after you arrive at an answer, now they're playing with one of the dimensions. Okay, they're going to start changing and then say, okay, what effect will that have? Well, that'll be one of those where you'll have to ask yourself, okay, did they just change dimensions on us? Is it just going to straight up double, or is it going, we're going to square something, or maybe even cube something? Is when it changes this measurement, is that measurement changing dimensions? Okay, so that's what the last part of it does. But to answer the question where it just says how many strands of lights are there, there's a lot of information. Like I said, you've got 6 structures in this thing, and all of them are unique. Okay, so you've got a lot of perimeters that you're going to have to figure out before you can simply say, here's how many strands of lights it's going to take. So what I've kind of done is I've broken it down. Question number 1, there are 8 distinct things that I think you have to address before you can answer the question of how many strands of lights it's going to take. Okay, first of all, okay, these first 6, these are the different perimeters. Okay, this is the different perimeters. So on A, okay, or one of the first things you're going to have to do, or one of the things you're going to have to do, is you're going to have to determine what is the perimeter of that hexagon. Shouldn't be that bad because they did give us a side length and they told us it was regular. So that's going to be pretty easy to come up with that perimeter. Okay, B, or another thing we're going to have to do, we're going to have to find the perimeter of the composite triangle trapezoid shape. That's going to be a little interesting because we can find perimeters of these figures, but since they're composite, we lose some of the side links of some of these shapes. So you'll have to put your thinking cap on to get the perimeter of the composite triangle trapezoid. C, another thing, there ought to be a gimme, circumference of the circular building. That should be easy because they hand you the radius. One of the other things, perimeter of the Pentagon. Okay, again, should be pretty straightforward because they do hand you the one of the side links for the Pentagon. E, you're going to have to find the perimeter of the composite building, that oval-shaped building. Okay, so the composite semicircle rectangle, we're going to have to find out how long that is around. Okay, well, we've already said it's kind of like a circle that's just been split into 2 semicircles. So we can figure out the circumference of a circle. That's kind of the left side of the building and the right side of the building. Then we got to figure out what's going on with that rectangle, that long length of that rectangle that connects the 2 circular ends. But also, one of the things, and I didn't mention this while we were doing it, the description of that building said, okay, on that atrium, the atrium is also to be outlined on the rooftop with the lights. Okay, so inside of that oval-shaped building, we're going to have to figure out what the perimeter of that rhombus is because it gets lights also. Okay, so the perimeter of the composite semicircle rectangle building plus the perimeter of the rhombus. So there's actually 3 shapes. You got the circle that's in there, we got part of the rectangle that's in there, and then we got the rhombus that's in there also. Okay, so there's a lot of information to think about on E there. F, another thing we have to know, the perimeter of the parallelogram. So yeah, we are going to have to find that missing side length for that parallelogram. After you do A through F, you will have all of the perimeters of all the different buildings. We're going to need to know a total perimeter of all the buildings so we can answer the question. So G says, okay, let's add them all up. Let's get our total perimeter and circumference. And then H is how many light strands does it take to cover that distance? Okay, so however big that number is on perimeter, okay, we're going to start hacking away at it at 16.5 feet. 16.5, take away 16.5, take away 16.5, over and over and over again until the building gets covered. Well, that's a division question. Okay, so whatever your perimeter is divided by 16.5 feet per light strand should tell you how many light strands it's going to take for them to answer the question. Okay, so there are, like I said, 8 kind of distinct things that I think you need to be able to address to answer this question. Okay. Now, question 2 says, since the businesses in the buildings are funding the purchase of the lights, the city is going to drop 250,000 flyers from helicopters to recognize the donors. How many of these flyers can theoretically be expected to land on the rooftops of the buildings around your answer to the nearest hundredth? Okay, well, in its own right, this is equally complicated, if not slightly more complicated than the first question. Okay, but it's not a perimeter question anymore. Basically, they're saying, okay, if we throw a piece of paper into the atmosphere above the building, okay, and it starts fluttering down, basically they're looking for a probability. What is the chance that it lands on the roof of one of the buildings as opposed to landing in the street around the buildings? Okay, well that's area. How much area is there covered by the buildings compared to how much area is there with the shopping center? Okay, well, the first six questions here are basically the same six questions as you did for question one, but only now we're not looking for perimeters, we're looking for areas. So we're going to need to know the areas, okay? The area of the hexagon, the area of the composite triangle trapezoid building, the area of the circle, the area of the pentagon. E has one key difference, okay? When we were looking for the perimeter of this shape that's got the atrium in it, we ended up adding in the perimeter of the rhombus in there because they wanted to put lights around it as well. Okay, but for an area question, we wouldn't want to add this area in because this area has actually been removed. Okay, technically, theoretically, they could drop the flyer could fall from the sky, and it could go down inside of the atrium. It could land in there. So that area, that area that's not grayed out there, that rhombus, that's not part of the area of the rooftops. So instead of adding that in, when it comes down to area on E here, you have to take that area away. Okay, so you're still going to have to find total area, and you're still going to have to find the area of the rhombus, only it's a difference of the two this time. Okay, F, find the area of the parallelogram. G, total up the entire areas that you've come up with. Okay, on H, okay, now we need to know what it's compared to, and that's where those measurements came into play. One of the things they gave us right off the bat was the total measurement, the total length and width of the shopping mall, and it was unclear why they gave that to us. Well, now it's not unclear anymore. We need to know how big the shopping mall is, because when we go to figure out the probability, we need to know what the total area of that space is. Okay. I, what is the probability that a randomly dropped flyer lands on a building rather than missing it? Well, probability, it's just a ratio. What goes in the numerator of the ratio? Whatever it is you're trying to get to happen, whatever it is you're observing, whatever it is you're studying, whatever it is you want, okay, that goes in the numerator, and in the denominator goes what is possible. So they're asking what is the probability that a flyer lands on the rooftop, so that is what is under investigation. Landing on the rooftop, that's your total rooftop area. And of course, the total area of the shopping center, that's your denominator. When you put that in there, you will get a decimal point that ranges between 0 and 1. 0 means there's no chance it lands on the building, okay? And 1 means that it is a total chance that is going to land on the building. Probability will be somewhere in between 0 and 1 after this step. Now, that's the probability that one flyer lands on the building, but of course they are saying how many flyers if we throw 250,000. So whatever your individual probability was on I, you will take that and you will multiply it by the total number of flyers that they do throw on J, and that should give us an idea of how many papers they should expect to end up on the roof rather than on the ground. Okay, so that is what we are doing today and tomorrow. As you can see, that's a lot more questions than meets the eye when you read that paper. Okay, but if you want to accurately arrive at an answer, you're probably going to have to go through all of these steps one at a time to get it done. Okay, so use the formula charts if you feel the need. Use the calculators as needed, and let's get started.